Founded scientists until the development of plate tectonics theory in the 1960s.
Plate tectonics is the overall model of how different parts of the Earth's crust are moving relative to each other. And the crust of the Earth is broken up into major plates. They slide past each other, and they move on faults. The San Andreas Fault is the major fault zone helping slide the North American plate past the Pacific plate. And this movement occurs at about 2.5 inches a year. Doesn't sound like very much, but over geologic time, it builds up into a lot of slip that has to be accommodated.
These great strides in understanding earthquake processes track directly back to the 1908 Lawson Report.
Perhaps one of the most important results that came out of this study was the development of Harry Fielding Reid's theory of elastic rebound. He used the information collected from land surveys that allowed him to measure the changes in land surface that had been caused by the earthquake. This was something that had been understood in rough form before the earthquake, but he developed the first scientific theory about how forces accumulate along faults only to be released in earthquakes. We call this the elastic rebound theory, and it's the foundation, really, of our modern understanding of the earthquake process.
If you can think of the crust as a slab of rubber, and you're grabbing the rubber from the two sides and moving it past each other, if the fault itself were Teflon, the rubber would just move by and never be distorted. But because the fault has friction, then the rubber gets distorted and stresses are built up on that surface. So that process is very, very slow, 1 inch a year, and suddenly, at the time of the earthquake, a very small piece of that high friction surface is going to let go. And as it does so, it starts slipping. And in the space of a few seconds, that slippage speeds up from 1 inch a year to 5,000 miles an hour. And that process then tears down the fault at these high speeds until it comes to a stuck patch where it can hang there for several seconds. If it's going to be a large earthquake, it's going to burst through, speed up again to 5,000 miles an hour, and go flying into the next knot in the piece of wood, if you like, hang there, and then burst through again.
In parts of California, we just really have the San Andreas Fault. It's the major feature. But in places like the Bay Area, the fault splays. It's like the trunk of a tree. It comes into the Bay Area, big branches come out. These are the major faults like the San Gregorio and the San Andreas and the Hayward and Rogers Creek, the Calaveras, the Concord Green Valley. And they accommodate most of the movement. And then even little faults come off of them, and they're like smaller twigs. Each different size fault produces different size earthquakes. And here in the Bay Area, we have many faults of different sizes spread out across the entire region.
Each of those faults could produce a damaging earthquake. In fact, taken together, we think a damaging earthquake is nearly twice as likely to happen as not over the next 30 years.
Earthquake information for the Bay Area, California, and worldwide can be found at quake.usgs.gov. Menu items link to things like Did You Feel It?, Shake Maps, and the Earthquake Information and Preparedness Handbook, Putting Down Roots. Science now gives us all a way to clearly see and understand the earthquake risk in our own lives.
Earthquakes are now reported as moment magnitude. So what happened to the Richter scale? Charles Richter and Benno Gutenberg developed the first magnitude scale in the 1930s to quantify earthquakes by relating the size or amplitude of seismic waves, shown on the right, plotted against distances calculated from S minus P arrival times, shown on the left. Connecting the two gives you the Richter magnitude. The scale is logarithmic, so a 1 unit increase in magnitude corresponds to 10 times larger amplitude. The limitation was that seismologists measured certain frequencies, which meant that the signals from large earthquakes weren't adequately represented, like not being able to hear the bass notes on your laptop speaker. That meant that the Richter scale underestimated the size of large earthquakes. Seismologists have since developed far more sensitive seismometers that, with faster computers, have enabled them to record and interpret a broader spectrum of seismic signals. These improvements allowed them to better determine the energy released by large earthquakes. In 1979, they connected the seismograph recordings with the actual physical displacements that occurred during an earthquake. The result was the moment magnitude scale. Seismologists no longer look at only the amplitude of seismic waves, but instead use much more information contained in the seismogram to calculate what is called the seismic moment. The seismic moment, which defines how much force is needed to generate the recorded waves, is defined by this equation: mu times distance times area. Mu is rock rigidity. It describes the resistance of the rock to bending when force is applied and is a constant for a given rock material. More elastic energy is stored bending rocks of high rigidity than is stored bending rocks of low rigidity. For example, this brick has high rigidity and when bent or sheared would yield a strong earthquake. The cake has lower mu and shears easily. Rock rigidity is lower in the crust than it is in the mantle. As mentioned earlier, in most cases, distance and area can be determined by mathematical modeling of seismograms. D is the distance that the rock slipped along one side of the fault zone relative to the other side. In the 1906 San Francisco earthquake, this fence line was offset over 3 meters. A is the estimated area of the fault zone along which the rock slipped, the distance d. It defines the area that actually ruptured during the earthquake. Let's watch an earthquake happen. The arrows show forces building on opposing sides of a fault. Growing stress that will be relieved in the earthquake will be shown in red. Here we see blocks of rock move in opposite directions along a strike-slip fault zone, such as the San Andreas Fault in California. Potential energy, in the form of elastic energy, is stored in Earth's crust or mantle, building stress as the ground slowly deforms between large earthquakes. Take a look below the ground at the earthquake rupture that defines the seismic moment. That equation is then plugged into the moment magnitude equation, which is used by seismologists to measure the size of earthquakes in terms of the energy released, not just the amplitude of the recorded waves. While the amplitude of shaking caused by a magnitude 5 earthquake is 10 times larger than for a magnitude 4 earthquake, the energy released increases by about 32 times for each unit increase in magnitude.